Hi folks, here is the Unit 2 Day 3 lesson. We're going to start talking about the dot product, which is one of the ways of multiplying vectors. And in today's lesson, we're just going to be looking at the dot product with geometric vectors. Tomorrow in the Day 4, we're going to do dot product with algebraic. So just to review from the previous unit, in Unit 1, we did a few different things. We looked at how to add vectors, subtract vectors, and multiply a vector by a scalar. But at that point, I said we weren't able to multiply vectors by each other. And there's actually not really vector multiplication as we would really think of it with real number multiplication. But there's two operations that are sort of similar to multiplication. So we give them different names and we give them different notation. So the first one that we're going to look at today is the dot product. And this is also known as the scalar product because it gives you a scalar answer when you dot, or in this form of multiplication, the two vectors together. The other form of vector multiplication is the cross product, and that produces a vector answer. It's sometimes called the vector product, but that's not as common to hear as calling the dot product the scalar product. So because we've now got three different kinds of multiplication involving vectors, it's very important that you keep the notation correct and consistent. So I'm just going to kind of review. In Unit 1, we looked at this one, scalar multiplication. So we had a scalar with, just kind of to clarify, k is a real number multiplied by a vector. And we didn't use any symbol in between there. We never put k times like a multiplication symbol, or we never put anything else. But there are different ways of showing multiplication just in real numbers, right? When you very first learn to multiply, you do stuff like this, right? 3 times 4. So we know that that symbol, the X, is obviously the most visible symbol for multiplication. Then once we start working a little bit with algebra, sometimes we start using things like this. A dot in between to symbolize multiplication. And sometimes you might just have like 3y. So if there's no operation or no symbol. So those are kind of all different ways of writing a multiplication operation. And we kind of use those three to, these are all kind of interchangeable, right? 3 times 4, 3 times 4, or if that was a 4, these would all be interchangeable. Having no symbol, having a dot, or having a multiplication sign. In the real number system, these all mean the same thing. So in real numbers, these are the same, but here they're not. We very specifically use these to distinguish between the three different types of multiplication with vectors. So when we had scalar multiplication, we never put an operation in there. We just have, say, 3u. We never put 3 times symbol u because it means something else. The dot product, this is what we're going to be doing today. You just put the little dot there. That tells you that you're going to have a vector dot a vector, and it will give you a scalar answer. And we don't say a vector times a vector. We're not going to use the language of times because that's actually not something that exists. Dot is a different operation than regular multiplication. And kind of similarly over here, we'd have u cross v. So if we have a vector and a vector with this cross symbol in between, and we'll get to that, I believe that that's day 7. Day 6 or 7 is a cross product. That will give you a vector answer. So you can see that both of these have two vectors with some kind of multiplicative operation between them. One will give you a scalar answer and one will give you a vector. So it is really important to just be clear in your notation about which of the operations you're doing. Okay. We're going to have different formulas, different methods for finding the dot product, depending whether we're looking at geometric or algebraic vectors. Today we're just going to look at geometric, and then we're going to use this one to derive the formula for dot product of algebraic vectors in lesson 4. So the dot product on the surface looks a little bit, when we get to the formula and the method, it looks a little bit arbitrary and random, and people might look at it and think, well, why are we even doing that? The dot product is not something that was kind of invented just for fun to say, what kind of weird math can we do with different vectors? And especially when we get into Unit 3, when we're looking at lines and planes and shapes in 3 dimensions, the dot product is going to be incredibly useful in calculating things about vectors and 3-dimensional space. So the dot product is something that kind of came about to solve a lot of problems like this. So we didn't set out to invent the dot product. We set out to solve some problems, and the dot product is a skill or a technique that we can use to solve them. So one of the main things we're going to be doing really right away is that the dot product is going to help us. This is probably the biggest one in this unit. It's going to help us find angles between vectors, and hopefully that's reasonably easy to understand why you might want to do that, or be able to analyze 2 vectors and see how they relate to each other. That's an important method that the dot product can help us with. Also breaking things down into component vectors. The later things, directions, equations of planes, will come in Unit 3. So here's what the dot product is. So again, geometric vectors, these are vectors that have that don't have a coordinate system. So they're just vectors in space. Now the dot product of 2 vectors is the product of their magnitudes multiplied by the cosine of the angle in between them. And remember, the angle between 2 vectors is always measured tail to tail. Okay, this is not going to look like it makes sense, but we will look at a diagram of these, because this, again, it seems super arbitrary. Why am I taking magnitudes and multiplying, and why is it the cosine and why is it not the sine? We'll show you with a diagram on the next slide, I think. So this is how we're going to calculate it for geometric vectors, but this is the really important piece here. It's important to kind of be able to visualize what is the dot product even measuring. So this is the really important bit. The dot product is measuring how much of a vector, so it's the length of one vector times the amount of the other vector that's going in the same direction. And I like to think of that as like, how much are these vectors helping each other? How much are they working together, or are they working apart? So the dot product is going to give us a scalar answer that's a number that is kind of representative of that. And I'll show you once we take a look at this equation what that means. So this, again, very important to have this equation. You will need to memorize this one. So u dot v is the magnitude of u times the magnitude of v times the cosine of theta, where theta is the angle in between them. That is super important equation. Write that one down, put some stars on it, memorize that for sure. Now this is what I want you to kind of take a look at. If we had these two vectors, so I'm going to label them. So u dot v. So if I had u and v, this is the dot product here is going to be a measurement of how much of v is going in the same direction as u. So from the equation, it's the magnitude of u times the magnitude of v times cos theta. I want to take kind of a closer look at this. This piece here, v cos theta. What would that be? So if I looked at the magnitude of v times cos theta, I know my theta is here, and if I was thinking about cos theta, might make sense probably to make a triangle involving theta. Now the cosine of theta would be this length here, kind of highlight this guy, over the magnitude of v. So I'm just going to label a distance in there. So d over the magnitude of v equals cos theta. So d would be actually this quantity, the magnitude of v times cos theta. I think I'm going off the screen there. So this tells me that this magnitude of v cos theta is actually this measurement. So it's how much of the vector v is going along vector u in this same direction. Like how helpful is v in terms of u? So you're multiplying u times the amount of v, or the component of v, that goes along in the same direction as u. So this is the size of vector u, and this part is how much of v, the component of v, that goes in the same direction as u. And I'm going to say helps you, because I feel like that's a good way to kind of conceptualize it, although vectors don't actually help each other. Obviously, that's not really math. Okay. So that is kind of a visual of it. This is the equation, and again, just for geometric, we will be looking at the algebraic tomorrow, but it's very important to kind of understand what this is measuring. So it's measuring one vector times how much of that vector is going along in that same direction. I also want to take a little look about what can happen with different angles for u and v. And I've thrown up the picture here of the cosine graph. The graph of cos, just to kind of think about what's happening here. So if they're perpendicular, then the dot product will be 0 because cos 90 is 0. So if I have these two vectors, So this is, I'm going to number the cases and kind of draw some diagrams down here. So if my theta is 90 degrees, so if these guys have a 90-degree angle between them, we'd have the magnitude of u times the magnitude of v times the cos of 90. But again, this is just here to remind you, cosine 90 is 0. So u dot v, in this case, would equal 0. So if you have perpendicular vectors, the dot product will be 0. And why is that? If we think about like how much of v is helping u, well, they're perpendicular. Is v helping the u vector at all? Is it going at all in the same direction? It's not. So it has like a 0 helpfulness in terms of going along in the u direction. The second case, if theta is less than 90. So here, if I were to draw these vectors out with an acute angle of theta, like that, then the magnitude of u is always positive, magnitude of v is positive. What's the sign of cos theta if theta is a less than 90 angle? That would be somewhere in here. So cos theta is positive. So u dot v is positive. So here cos theta equaled 0. So that's my second case. And then the last one, I'll do a diagram down here for the third case. What if the vectors had an obtuse angle bigger than 90, between 90 and 180? And again, just sorry, kind of flipping back to this one. This vector v would have a positive, helpful impact. If we said how much of u is helping v out, it would be a positive amount. There's some amount of v that's going to be working with that blue vector there. And the last case here is if theta is bigger than 90. Just a note, theta can never be bigger than 180. If it like looped, if vector v looped around and you were trying to measure like a bigger than 180, you'd actually just measure the other direction. So it can never be bigger than 180. So here, if theta is between 90 and 180, that would be in here, and we would have a negative value for cosine. So cos theta is negative, less than 0. So then that means u dot v is less than 0. And if we think of that in terms of the kind of helpful analogy, how much is v helping out u? If you imagine these as forces, or you imagine these as like wind, like our previous two lessons, right? If u was a force acting this way, how helpful is v? It's unhelpful. It's like a negative amount helpful. If u is the plane flying this way, how helpful is that wind? It's not helpful at all. It's actually working against it. So it would have a negative dot product there. Just a quick note, when we're doing all of our work in vectors, we're going to be using degrees, but there's no reason you couldn't work in radians. The standard though is degrees. So we're not going to be really working in radians for any of the vectors work. But since you're just finding the cosine of the angle, if you had radians, that would be fine too.